In our study of chemical kinetics, we've already encountered something called the rate law equation. And the rate law equation is a formulation that tells us about how fast a reaction is going. And it has this form where the rate of the reaction is equal to a reaction rate constant, a proportionality constant, times the concentrations of the reactants. And just to keep things general here, we'll say that one of the reactants was A, another B, and another C. But as you know, these A's, B's, and C's may actually have exponents as well. And I'll say that A is raised to the second power, B to the first power, and C to the 0th power. We can say then, with words, that this is a reaction that is second order in A, first order in B, 0th order in C, and third order overall. Now, in this lecture, what we're going to do is look at something called the integrated rate equation. Now, the integrated rate equation is something different because it answers a very different question. It tells us how much reactant is left over after a certain amount of time. It doesn't tell us anything at all about how fast it takes for us to get there, but it does tell us how much of the reactant is left unreacted after a certain amount of time has passed by. Now, we'll get into the details here in just a moment, but another term that's going to come up as we discuss the integrated rate law equations is the notion of half-life and the half-life equation. And the half-life equation tells us how long does it take for half of the reactant to be used up. How many seconds, minutes, or hours needs to go by before half of the reactant that was originally present still survives in whatever reaction container we're referring to? How long does it take for half of it to go away? All right, well, let's have a look at the first of three different integrated rate law equations. We call this the 0th order integrated rate equation, and it would refer to the following situation. Let's say that we did the necessary experimental work and determined that the rate of the reaction was equal to K, the reaction rate constant, times the concentration of a single reactant raised to the 0th power. This is an example of formulation that is 0th order, as we know from that superscript above the X. Now, as we continue with this, we can do experiments, and in an experimental situation, what we find is we begin with a certain amount of X at the beginning. This would be the concentration of X with a little 0 down there to suggest that it's the initial concentration of X. All right? And then my x-axis tells me about what happens, or it tells me about the progression of time, and that as I'm waiting longer and longer, the concentration of X might be changing, and I'm moving further to the right on the graph. And for a 0th order reaction, what we find is that the amount of A steadily decreases, but decreases in a special way. As you can see, it's decreasing in a linear fashion. This is, in fact, a straight line, and something we need to recognize about 0th order reactions, namely that the concentration of the reactant decreases, as we would expect since reactants are used up, but decreases in a linear fashion, following a straight line, if we graph the concentration of X at various points in time. Now, straight lines are exactly what we're looking for here, because the formulation, the arithmetic regarding straight lines, is well known to us. And in fact, experiments and theory have shown us that we can actually write an equation for this line. The equation is going to relate the concentration of X at some time t that we're free to pick and choose whatever we would like, and that concentration is going to be equal to the negative rate constant K, that's right, the same K that we associate with the reaction rate law, times T, T is standing for time in this case, plus the initial concentration of A, not to be confused with the other one. I'll put a little 0 down here to tell us that is the initial concentration of A. All right, so we've got the initial concentration here. We have time there, we have the rate constant K there, and we have the concentration of X at any other time that we can think of. And this would then describe the behavior that we see in the graph at left. Now, it doesn't hurt to review with you a little bit of the arithmetic going on behind the scenes here. We're going to associate X at time t with what's happening on the y-axis. And we're going to associate the negative K piece of this as M, the slope of that graph. And we're not really dealing with, we're dealing with t's, but in the old-time favorite from our math classes, the slope-intercept form, we recognize that t, the independent variable, is actually the x in this case. And then we have this piece over here, which is commonly known as the y-intercept, or in that equation that we all know is b. And so we can see that from this integrated rate equation, it actually is an equation that fits the form of y equals mx plus b. Which means that what we can do is we can return to our graph and derive some really important information. Now, if we go back to the graph and we recognize that with a complete graph with numbers, why, we could determine the rise and the run of that graph, and we could determine the slope of that straight line. The slope, of course, is m. But the slope of that straight line, if the graph is what we have to work with, the slope of that straight line is also equal to a negative k from that association off to the right. That's right. In this case, with the graphical information, we can simply calculate the slope of that line, take the inverse of it, or not the inverse, but the negative of it, and we'll have a value for the reaction rate constant K. And so the graph actually delivers on some rather important information. Now, another thing that we can recognize from this graph, or from this situation, is the half-life. Now, the half-life is the amount of time it takes for half of X to be gone and half to survive. And so we'll look at the half-life here, going up from 0, which is in the lower left-hand corner, of course, going up to the halfway point. We can see that that line corresponds to an amount of X that is half of the original amount, and then if we extend this line down just like so, we actually have, for that point right there, the time that we could read off the graph that would be t1/2, otherwise known as the half-life. The amount of time it takes for half of A to be gone. In this case, you can tell that by waiting an additional amount of time equal to the half-life, we would have no X left whatsoever. But it's the half-life that interests us at this point. And from algebra and calculus, it has been determined that the half-life for a first-order reaction, very important that this works for a first-order reaction, is something that we can calculate and is equal to the concentration of X initially divided by 2 times the reaction rate constant K. Now, it's also important to remember that, and we'll look at examples of how this works a little bit later on, but note that the half-life includes the initial concentration of X. It does depend upon the initial X concentration. And if you think about it, this just stands to reason. Doesn't it make sense that if you have more X around as a reactant, wouldn't you think it should take more time to use up half of it? It sort of makes sense that that's the way things ought to work. And in the case of a 0th order reaction, that is indeed the case. These two formulae, the integrated rate equation and the half-life, you need to have some working experience and you need to have committed to memory. Now, we're going to move from the 0th order reaction to what's known as a first order reaction. The first order integrated rate equations, what we're going to look at next. Now, what would the rate law equation look like for such a situation? Why, the rate would be equal to some reaction rate constant K times the concentration, let's stay with X to keep things general, All right? The concentration of X raised to the first power, just like that. Okay? And so this is a reaction that, if it indeed follows this rate equation, is first order in X. First order in X. Now, don't forget that X is a reactant after all, and we expect reactants to be used up. Previously, we saw that the amount of X in the 0th order example did decrease as time went by. And indeed, we find that that is the case now as well. We begin with, as we did before, an initial amount of X. I'll call that X0. It starts high, and we know that as time goes by, it's going to be used up. But what's interesting about a first-order reaction is that the behavior that we observe is not behavior that is linear. In fact, there's a significant curve to it. And because of that, we're unable to really derive a simple mathematical relationship that describes how X depends upon time. We're not fortunate enough in this case to have a straight line. However, a little bit of work on our part and some other graphing attempts will show us that if instead we graph the logarithm of the X concentration, instead of the X concentration, the logarithm of the X concentration, why, what we observe is that the behavior now is straight line. And so we can obtain a straight line relationship that relates the concentration of X to time if instead of an X versus time graph, we plot a natural log, an ln X versus time graph. Now, the point up here clearly is not the initial concentration of X anymore. It is, in fact, the natural logarithm of the concentration X initially. And so an important distinction to make here, we are definitely looking at a very different graph, but a straight line, and that is encouraging. Now, we can also write out an equation for this first-order integrated rate law, and that includes that the natural logarithm of X at some time t will be equal to a negative k times the time plus the ln of X initially. Just like that. That is the integrated rate equation for a first-order reaction. And, as we did previously for the 0th order, what we can say is that this thing to the left of the equal sign relates to y of the slope-intercept form. We have negative k, which is relating now to our slope, m, as it did before. Time relates to the x. And this entire piece here, ln x0, relates to the y-intercept b. All right. And just as we did before, we can actually learn quite a bit about the situation if we simply look at the slope of the graph. Measure a rise, measure a run, calculate a value for the slope, for m, and that value that we obtain for the slope from this graph will be equal to a negative k, just as it was for the 0th order reaction, but do note the difference. In the case of the 0th order reaction, we were using an x versus time graph. For a first order reaction, if it's a first order reaction anyway, we will be using an ln x versus time graph. But again, the graph gives us a way of determining the slope and thus the reaction rate constant k. Well, that's the first order integrated rate equation. We still need to say something, though, about the half-life. And the half-life, in this case, put that over here, the half-life, the definition hasn't changed at all. The half-life is the amount of time it takes for half of the material to go away, and in the case of a first-order reaction, the half-life is calculated in the following way. We take the natural logarithm of 2, and we divide it by the reaction rate constant k. And you should note something about this half-life for a first-order reaction, and that is that it is independent of initial concentrations, which is a little strange when you think about it, because it's saying that the amount of time that it takes to completely use up half of the initial starting material, X in this case, doesn't depend upon how much of X you have initially. In fact, it is a fundamental characteristic of it being a first-order reaction, and the half-life is independent of time. Now, let's imagine the following situation. Let's think, to begin with, that we have at the start a certain amount of X. And I'll demonstrate this in a bar graph sort of way. And so here is the amount of X that we've got. And I'll say that the X concentration in this case, the initial X, is equal to 1. Now, we don't actually have a number for the half-life, but we can at least think about it in the following way. If we wait an amount of time equal to 1 half-life, then how much of X is going to be left? Well, the half-life, by definition, is the amount of time it takes for half of it to disappear. And so there should only be about half of X present at the end of 1 half-life. And so if we began with 1, then the amount of X we're left with in this case is now 0.5. Give it some units, molar. This only works for first-order reactions. If we wait another period of time, another half-life, then the amount of X that we have will be half of the amount that we had previously. Will be now down to 1/4 of X remaining. And you can continue this process as far as you would like. The idea is always the same. With every subsequent half-life, another half of the previous amount is taken, and so this would be 0.125 molar left. And you might be wondering, well, is there ever going to be an end to this? And the answer is nope. In theory, this reaction will continue taking halves as long as we care to continue the process, and at the end we'll always have still some significant amount, or small amount more likely, of X left. This is in fact the same type of process that radioactive decay exhibits. Radioactive materials decay via first-order reaction kinetics. Consequently, if you have a radioactive piece of material, say a 1-pound piece of radioactive material, and it has a half-life of 10,000 years, you'll have to wait 10,000 years, and at the end of that time, half of that pound will be left. You'll have to wait another 10,000 years for there to be 1/4 of a pound of material left, and so on and so forth. And so for these materials that have very long half-lives, you can see the dilemma we face in that it does take a very long time, in some cases, for the material to decay to safe levels. All right, enough about first-order reaction rate kinetics. Let's talk about second-order integrated rate equations. Second-order integrated rate equations, in this case, we're going to have, just as an example, the rate of the reaction would be known to depend upon our reaction rate constant friend again, and a concentration of X. This time, though, raised to the second power. We would say that this reaction is second order in reaction in X. Now, previously we found that a simple plot of X versus time was linear in the case of 0th order. It wasn't linear, rather curved actually, in the case of first order, and that trend continues. The curvature, again, starting with some amount of X up here at the start, we do see that the amount of X decreases. It's a reactant. It ought to go down. However, in this case, it doesn't go down quite as fast as the first order process did. And never mind that, it's not a straight line, and a straight line is really what we're all about. We're hoping to have straight line behavior because from a straight line, why, we know that we can derive some important information. And so the question is then, in this case, what do we graph to obtain a straight line? And for second-order integrated rate equations, it turns out that what we need to graph is the reciprocal of the x concentration versus time. And when we do this, we do get a straight line, just like this, where this point right down here, where it crosses the y-axis, is a point where the initial concentration of A is some known value, and this is, or of X is some known value, and this is the reciprocal of the concentration of X initially. Okay, but it's a straight line, and straight lines, well, we can work with those. The second order integrated rate equation goes something like this. We have 1 over the concentration of X at whatever time we're considering, and that is going to be equal to K times T plus 1 over the concentration of X as it was initially. This is an equation that also fits the pattern of slope-intercept, where 1 over xt is actually the y in this case. K in this case is the value of m, and note that it's a positive k in this case. Previously, for zeroth and first order, the k had been a negative value, but in this case it's a positive value. T relates to whatever x happens to be, and then this entire reciprocal of the initial concentration of x becomes our y-intercept, and that was actually indicated on the graph at left. All right, now we can also return to our graph. If it's a second-order process and we graph 1 over x versus time, why, we'll come up with a straight line. And the slope of this straight line, otherwise known as m, is in fact equal to the reaction rate constant k, with no sign change in this case. This sets it a little bit, makes it a little bit different from the previous examples that we've looked at. To finish this off, we have to say a word about the half-life, and the half-life for a second-order reaction can be calculated, again, and is known to be equal to 1 over K, the reaction rate constant, times the initial concentration of X, whatever that happens to be. Note also that just as it was the case for the zeroth order reaction, the second order reaction half-life also does depend on the initial concentrations. And so the first order reaction is the only one for which the half-life does not depend upon the initial concentrations of any of the reactants.